I will demonstrate this with an example. Is it clear so far, though? So, yeah.
Just a question about the dimension. It's not better to make an equation dimensionless, like is that the dimension non-dimensional?
Yeah, you can make it non-dimensional. Yeah.
For the conversion, which one is better? If we make or normalize the data, it's not better to have a better conversion, or it's because T may be so high or something?
Okay, so if I get your question properly, you're asking if you don't non-dimensionalize in the convergence, the quantity or the error it's calculating is going to be dimensional, and how is that then going to be handled?
Yeah.
Okay, that's a good question. So how it is handled is if you don't dimensionalize in the solver sequence, you pick a scaling for your independent variable. So you can specify a scaling, how it should scale it. So it will actually divide the solver when it calculates the error before it puts it into a tolerance. It will divide it by the scaling you provide.
Then I don't need to change my equation, right?
No.
Just use all of them in the term of the have a dimension. It's okay.
Yeah. You have dimensions, and then in the convergence check you would put a scaling.
Okay.
Yeah. Does that answer the question? Okay. So let's say we want to model the Poisson equation to start simple. With a boundary condition 0, Dirichlet boundary condition 0 everywhere. Now, the way you use these templates is by just matching the templates with the equation you have. What is the template? The template is this, what we have in the domain. But what is your equation? Your equation is the first equation, so you don't have all these terms. What do we have? If you have C is equal to 1, and F is equal to 1, and everything else 0 in that equation, you get the Poisson equation, right? With the source term being 1. So then you are set in the domain. Then now you want to pick what happens in the boundary. So for what happens in the boundary, this is going to be a Dirichlet boundary condition. The template is going to be U is equal to R. Then here what we have is R is equal to 0. So just put R is equal to 0, and you are done. So I will now go into the software and show how to enter this. Is it clear so far? Okay. So if I start the software here, when you start a new model, as you would have seen on Monday, you can start with a model wizard or the blank wizard. If you start with the model wizard, the first thing is you have to select your special dimension. Let's say we are going to do a 2D problem. Then you pick 2D. Then you pick your physics, but in this case, you're not going to use any of the pre-built physics-based interfaces. You are going to use the mathematics interface. And you come here, you come to PDE. We're going to use the coefficient form now. I'll show you the general form later. So you use the coefficient form, add that. And here you can decide what to call the independent variable. So by default, it wants to call it U. But if you're, for example, solving a temperature problem and you want this to be similar to the units you have, the variable name you are using often, then you can rename it. And here you specify the units for the dimension and for the source term. So let's leave this as it is now. Study. Then you pick your study type. Are you doing a stationary study? Is this an equilibrium problem where the time derivatives are all 0 now? Or is this a time-dependent problem, an eigenvalue problem? So let's say this is a stationary problem. Yes?
The equation is the stationary. It's not time-dependent because the equation.
Yeah, but at this point, we haven't really specified the equation. All we have said is we want to use equation-based modeling, right? Yeah. But that's a good concern. I'll show you what happens. So here you would define your geometry. Let's say we just want to solve this on a unit square. And I right-click on geometry, pick square, pick the dimensions 1 by 1. Let's say the default was 1. So this is my domain. Now the next thing is, there are 3 modes here: your equation, your default boundary condition, and your initial condition. Now let's go to the equation. this is the equation. And if you expand this equation section here, you will see the template. So it's saying it wants to solve this. Now you have to specify what is C. C is in our case 1, so we keep C is equal to 1. If we had no source term, we will come back and put this F to 0. Then, okay, now I have EA set to 0 by default, DA to 1. But these values are 0, right? I can type the 0, but I can also not type them, because in a stationary study, it will ignore the time derivatives. So let's say I actually had a non-zero mass term. First, I want to solve it for a stationary case. Next, I want to solve it for a time-dependent case. So instead of putting the equation twice, I can just add another study, but make that study time-dependent. So the stationary study will ignore the time derivative. The transient study will keep the time derivative. Does that address your question? Yeah. So yes, I can put this to 0, but the time derivatives are ignored anyway in a stationary study. And then you can check this other coefficients. They are all 0. What we want is this. Now actually we're just solving the Laplace equation since I put F is equal to 0. Then the next thing is the boundary condition. The boundary conditions are setting the Neumann boundary condition to 0. That's the default. So basically, physics-wise, that's no flux of the quantity you are conserving. So in a chemical reaction problem, this would be no concentration crossing the boundary. In a structural mechanics problem, the momentum flux being stressed, it would mean free of stress. But if your boundary conditions are different from the default, you specify them. So if I right-click here, right, on the physics or on the equation, these ones are things I could do on the domain. But these ones are boundary condition. So in our case, we have a Dirichlet boundary condition. I click that. Then you choose where to apply this. I could keep clicking, but if you are applying them for all boundary, you can also use this all boundaries. Then what is this? What is your solution outside? We are using here U is equal to 0. So if I specify that is already 0, then you build your mesh, and now you solve. Now this is going to give me a 0 solution back. I'm solving the Laplace equation with 0 boundary conditions. But what we wanted to do was the Poisson equation. So if I go back to the coefficient form and put F is equal to 1 and solve that, what? I put the boundary condition. I put constraint. I should have put the Dirichlet boundary condition. All boundaries. Okay. So this is the Poisson equation with source terms equal to 1. And here I can post-process it for other quantities, maybe make a contour plot, or maybe here instead of just the surface, add a height expression. This would be my solution. But the idea is, if you're using the coefficient form, you just come here in the equations template, and then you fill in these terms so that the template matches the equation you have. Here I have initial values. In a time-dependent problem, those are physically meaningful quantities of where did you start, where are you starting, what was the state of your problem at t is equal to 0 or whenever you start solving this problem. But for a stationary problem, they don't have any physical meaning. But can you think of a way they can be useful? Any guess? Yeah. Can you make it more? Can you elaborate more?
Convergence and next integrations.
Exactly. So these equations are potentially nonlinear, right? In this case, you win the first time. In this case, we are solving a linear problem. But think of solving this nonlinear problem. What happens? The weak form will convert this, and then when you add the finite element discretization, at the end what you will have is a system of nonlinear algebraic equations for the nodal values. So when you have nonlinear algebraic equations, you're going to solve them using a Newton-Raphson or other method like that. And there, you're going to start with an initial value and iteratively try to get to your solution. So even though this initial values node is physically meaningless for a stationary problem, you can nudge, if you have any a priori information, if you have some estimate about your solution, you can type that in, and then it will help the solver converge faster. Or, this is assuming you have a unique solution. In cases where you have multiple solutions, you can also use this initial value to sort of bias, right? It will most likely converge to the solution closer to the initial value you are putting in. Okay.